Now we're going to take a look at what we know about the neural basis of consciousness itself. So consciousness can be a difficult concept to define. It is sometimes defined as a state involving awareness of something, so that consciousness is consciousness of something else, awareness of something else. It's thought to involve the spreading activity from the thalamus to the cortical areas. And so that's one thing that we're going to be learning about, that consciousness is associated with the spreading of activation. So if we hear something or see something or feel something, that the thalamus, which first receives that information, is going to increase activity then in other areas of the cortex. Now we look at how the brain underlies consciousness and how different types of brain activity are involved. We can think about these different networks. So remember, instead of looking at just isolated brain regions, we want to start thinking about how different regions work together and some of the connections between these areas. And so we're going to look at the salience network, shown here in blue in the middle brain scan here. And this area switches back and forth. So it's sort of in charge and sort of switching back and forth between the internally directed default mode network, shown here on the left brain scan in yellow, and the task-oriented, externally directed central executive network, shown here in green on the brain scan on the right. So the switching from one mode to the other by the salience network seems to involve the anterior cingulate cortex and the anterior insular cortex. So we're seeing here the ACC and the AIC, the insular cortex and the anterior cingulate cortex. These are both areas that are in the midline, so they're buried in the middle of the brain, and they are involved in sort of this direction or kind of control of these other two networks. Remember the default mode network? That's sort of our at ease type of network, when we're ready but relaxed, kind of more internally focused, kind of daydreaming is sort of associated with the default mode network. And in contrast, when we're focused on an outward task, we need to use the central executive network that is going to involve the dorsolateral prefrontal cortex and the posterior parietal cortex here. Now, when we are paying attention to something, when there is this focused attention to something, there have been studies that have looked at the types of brain activity that we see. And here's an example of synchronized activity again. So we've seen in this chapter already other examples of synchronized brain activity during sleep, where like the hippocampus will have a certain type of brain activity that corresponds with, say, neurons in the motor cortex, for example, that are replaying something that we may have learned to do earlier that day. So remember, that's the kind of activity we're looking at, where the neural activity in more than one area is sort of showing the same timing, the same pattern. So we're seeing this kind of synchronized activity now when we are paying attention to something. And how did they do this? Well, they got people to pay attention to something like this light by pairing it with something aversive, in this case a shock to the middle finger. And once you do that, of course, we have basic classical conditioning. When the person sees the light again, it's going to remind them that, oh, a shock might be coming. If the shock came to the left finger, we can see that when they see the light gets turned on, there is synchronized activity in the visual cortex back here, of course, corresponding to the light, at the same time that we see synchronized activity in the somatosensory cortex on the right hemisphere of the brain. Why the right? Because the shock came to the left finger, and remember, the right hemisphere of the brain is the one that is involved in processing the sensory information to the left side of the body. Now, when instead the shock was delivered to the right finger, we can see that synchronized activity spread from the visual cortex to the left somatosensory cortex. So we're seeing that synchronized activity then is one hallmark of consciousness, and it allows processing of information in different parts of the brain to be connected in that way through that synchronization. Now, another aspect of consciousness involves our sense that we are in charge, that we are in charge of our actions, that we are the ones responsible for them. We can think of that as a sense of agency. And so in this case, brain imaging was done when a movement of a cursor on a computer screen could be either controlled by the person or not. And so when it seemed that the individual was controlling that cursor, and they attributed the cursor's movement to their own actions, the insula became active. When instead it seemed that someone else was controlling the cursor, then we see that the insula is no longer active, but instead the inferior parietal cortex becomes active. So when I'm doing it, it's my insula that kind of kicks in and demonstrates this kind of activity, that sense of agency. But when it's attributed to someone else, then it just gets processed by the parietal cortex. Now we'll take a look at disorders of self. And these are typically not due to naturally occurring situations, but the result of a split brain operation. This is a surgical separation of the two hemispheres, of the left and the right hemisphere. This was something that would have been done more frequently years ago as opposed to now, and usually in response to epilepsy that was difficult to treat with drugs.
I know the left hemisphere and right hemisphere now are working independent of each other, but you don't notice it. Now, you just kind of adapt to it. You don't have any feeling, it doesn't feel any different than it did before.
7 years ago, Joe had brain surgery to allay the effects of severe epilepsy. His surgeon cut the nerve fibers connecting his left hemisphere with his right. While the operation was a complete success, Joe's unusual case offers an extraordinary insight into the machinery of mind. This fiber system, the corpus callosum, is located midway between the two hemispheres. When it was surgically severed in Joe's brain, the transmission of information between the two hemispheres was halted. Michael Gazzaniga.
What we can do is play tricks by putting information into his disconnected, mute, non-talking right hemisphere and watch it produce behaviors. And out of that, we can really see that there is, in fact, a reason to believe that there's all kinds of complex processes going on outside of his conscious awareness of his left half brain. Joe, I'm going to show you some things. I just want you to tell me what you see. And here we go. You ready? Look right at the dot.
Okay.
Right. Okay, you ready? Look right at the dot.
Grapes.
Good. When Joe focuses on a point, look right at the dot, everything to the right of the point goes to his left brain, the dominant hemisphere for language and speech. Look right at the dot. So we can see here that when we flash a word or a picture, Joe is easily able to name it. Here we go.
See it.
Close your eyes and let your left hand do a little work here. Okay, what do you got there?
Pan.
Okay, very good. Now, when a word or a picture falls to the left of a fixation point, that information goes to his disconnected right half brain. And as we can see here, Joe is unable to name it. Joe is able to draw the picture with his left hand, the left hand getting its major control from the right half brain. What did you draw?
Okay.
What did you see?
Wheel on one side. I don't know where I saw it.
So even though he can't name it, his left hand is able to draw out a picture of the stimulus, of the picture or word that we presented to his right half brain. What did you see?
Saw a hammer.
So just close your eyes and draw with your left hand. Just let it go. That's nice. What's that?
Saw?
Yeah. What'd you see?
Hammer?
What'd you draw that for?
I don't know.
What we have with Joe is just a dramatic example of a neurologic case that really allows you this window into the non-conscious and how powerful non-conscious processes are at influencing our conscious self, our personal self. What Joe and patients like him, and there are many of them, teaches us is that the mind is made up of a constellation of independent, semi-independent agents, and that these agents, these processes can carry on a vast number of activities outside of our conscious awareness. Even though that goes on, there's some final stage or some final system, which I happen to think is in the left hemisphere, that pulls all of this information together into a theory. It has to generate a theory to explain all of these independent elements. And so, and that theory becomes our particular theory of ourself and of the world.
So let's summarize how this works. Input from the left field of view is processed by the right hemisphere of the brain, in particular the right visual cortex. Anything on the right side of the world would be processed by the left visual cortex, but because the corpus callosum is cut, the two hemispheres can't share that information. And so if the person is asked a question, only the left hemisphere can respond verbally, because only the left hemisphere in most people is capable of speech. Therefore, if the information was shown on the left side and processed then by the right half of the brain, the left hemisphere cannot answer that question. It didn't see the information. But if the left hand is provided a way of communicating, for example, by drawing, it can then communicate that information.